Now that we've kind of introduced the concept of equilibrium, let's actually look at a couple of equilibrium problems. So we'll do one in this video, we'll do one in the next video. Now, these problems, they're very special cases, and I'll explain why in a moment. So for these equilibrium problems, sometimes you'll actually find it much more advantageous to draw a vector diagram, and you're going to find that for certain questions, if you can find a right angle in your vector diagram, you can use Pythagorean theorem, you can use SOHCAHTOA. So the questions that we have here that we're going to do, if we draw a vector diagram really carefully, we'll actually get a right triangle, and that will make life a lot easier. And the reason that we're going to get a right triangle is you have to remember that in an equilibrium problem, the net force is going to be 0. So if we draw a vector diagram of forces and the net force is 0, we're going to end back at the place that we started. That means if we draw our shape, we're going to draw the shape, but we're going to have to come back to our starting point. So we're going to have a closed shape. Because we're going to be dealing with problems with 3 vectors, we're going to have a triangle, and the angles that we're going to have in these triangles, they're going to give us a right triangle. Now, if this is not the case, you'll have to do a more advanced technique. Well, I would say more advanced. You just got to do one that's a little bit more mathematically laborious. But I will have a video for that. It's meant more for my IBs, but if you're a regular student and you want to see how that's done, go to it. It's not a bad thing to know about. So let's have a look at one of these questions here. So we have a store sign. It's experiencing a downward gravitational force of 245 newtons. So they're telling you Fg, and it's suspended as shown in the figure below. So we want to find the magnitudes of the forces of tension. And we want to find Ft1 and Ft2. And we're going to draw a free body diagram for this. Right, well, it's telling us to draw a free body diagram. It shouldn't have to tell you that, because as a free body diagram, you should always be drawing the free body diagrams to begin with. So what do we have going on here? Well, we certainly have a force of gravity. That hasn't changed any. So Fg is still going down. So I have that force of tension 1 kind of working its way away here. So I get this Ft1. Looks a bit like that. Actually, probably should be a little bit longer here. Yeah, I'm not doing the best job at sketching this. Trying to keep them relatively close to one another. Alright, so that looks like an Ft1, and then Ft2, well, let's say it looks a bit like this. Let me just kind of explain my rationale for drawing these. This thing is in equilibrium, so we need the net force in both directions to be 0. So in the x direction, I'm going to need this force to be balanced out by the x component of this force of tension 1. So I want this x component to be roughly the same length as that. In the y direction, I want the force of gravity to be balanced out with the y component of Ft1. So I'm trying to draw them roughly to scale. Not the best job, but hey, it is what it is. Now, at this point, you have a free body diagram. Let's draw a vector diagram. Now, because we actually have a right angle in here, you'll notice that Ft2 and Fg, they're at right angles to one another. What that tells us is that whenever we draw our our vector diagram, we will have a right angle in there. That opens up a lot of tools. It opens up the Pythagorean theorem, and it opens up SOHCAHTOA. That's helpful for us. So let's draw the vector diagram. Now the vector diagram, we have 3 forces. Here is the good news. You do not need to draw them in any particular order. You can draw them however you see fit. So for me, you know what I'm going to do? I'm just going to draw them Fg, Ft2, Ft1. The order you draw them in does not matter. So I'm going to start with Fg here. So I got Fg. And then at the tip of Fg, let me draw an Ft2. So it's going directly to the right. So we got Ft2. And now, because this is an equilibrium and my net force is 0, when I draw my last vector here, its tip has to get to the starting point. So basically, we're going to make a closed shape here. So that's Ft1. So because we're in equilibrium, we're going to have a closed shape. So our last vectors, the tip of our last vector is going to be at the tail of our very first vector. So we have a nice right triangle. This is really good. The only thing that we need, though, is we need some more information. So we're actually told FG, we don't even have to calculate it. We're actually told that this is 245 newtons. So I have this side of the triangle here. The only way to get one of these two sides though is I need another angle. I have this right angle, but we're a little bit hooped for the moment. But careful, we can really work this out. You'll notice that FT1 in my diagram, you'll notice that it's angled 40 degrees below the horizontal. Like if we go 40 degrees below the horizontal here, that's where our vector is going to be. We can actually kind of apply the same rationale to our diagram here. So if I see my vector, so this is like my horizontal here. We know that, if we know that that angle there is 40 degrees because this vector is 40 degrees down from the horizon. That's good. That's very helpful. But we usually want an interior angle of the triangle. But that's also going to be pretty easy for us to get. This angle plus this angle are going to make a 90-degree angle. So we're looking for the complement in here. So this angle should actually be 50 degrees. Or I guess it should be 50.0 degrees for sig digs. And that should be 40.0 degrees. So that's the way we can actually incorporate the angle in here. So you have to be really careful with your drawing. You may get it that your interior angle is 40 degrees if you draw your vector diagram a certain way, but just be mindful of how you draw it and just use all your like little knowledges of geometry and stuff. So we have this vector diagram. We have this angle of 50 degrees. So knowing this angle of 50 degrees, let me label my triangle. So I know this side is going to be my opposite. FG is going to be my adjacent. And then FT1 is going to be my hypotenuse. So to find FT1, I know my adjacent and I have my hypotenuse. So to get FT1, I know that cos of my angle, it's going to be FG divided by FT1. Or I could say that FT1 is FG divided by cos of my angle. So we know FG. FG is 245 newtons. And then I know my angle is 50 degrees. So I could say that the magnitude of this thing is about, let's see here. So it's about 381 newtons. We haven't been asked for direction. Don't worry about it. Now, also looking at my triangle here, I see FT2. Now, I've calculated FT1. I probably don't want to use that for calculating FT2, just in case I got that wrong. So for FT2, I know my FT2 is my opposite, FG is my adjacent, so I know the relationship I'm going to want to use here is tangent. So I know tangent of my angle is going to be this magnitude of FT2 divided by FG. Or I could say that FT2 is just going to be FG times tangent of my angle. So we know that FG is 245 newtons, and then we got that tangent of 50 degrees. So this is going to give us about 292 newtons. Again, we were not asked for direction, we've just been asked for magnitude. So we have our two forces of tension. We're told FT1 is 380, or we found FT1 is 381 newtons, and the force of tension 2 was about 292 newtons. Now, we were allowed to use this trick with the vector diagram and right triangles because we managed to make a right angle. The next question we do is also going to have that. It's going to be a little bit trickier to see, but then I will also show another video where you cannot use this trick and how you would actually approach that. It'd be a little bit more mathematically intensive.